did it. We're here, and this is lecture 12. So, are there any questions so far? Start with a bad joke. Okay, so here we are in the class. So we've done the midterm. The midterms, I will talk a little bit about the midterm in a minute. Today we're going to be talking about channel capacity, which is an extremely important topic, and it's really the second half. We're going to get today and Thursday and some of next Tuesday into the main, proofs and theorems associated with channel capacity, and some of it we're going to definitely, part of the problem, part of the class is to understand Shannon's proof. It's really one proof that we're going to spend like a day going through. So I would strongly suggest reading ahead in the lecture notes so that when you come to class, you have seen it before. Or alternatively, I would suggest watching these lectures several times since you have that opportunity to watch them on YouTube. We've got outstanding reading, which everyone should be reading regularly. In addition to your problem set, in particular, you should be reading chapter 7 in the book. That's the one on channel capacity. And I guess there's homework. I mean, it actually is out. It's out and it's due on Thursday, which is 2 days from now. I want to mention a couple of announcements. Oh, you know what? I just realized something. I think this is. I made a mistake in today's lectures, but we'll just have to suffer. Here, just a couple of announcements. So first of all, office hours, I've moved them to Thursdays right after class rather than Tuesdays, because the homeworks are going to be due on Thursday nights rather than Tuesday nights. I figured that maybe you would find office hours more useful, and maybe more people would show up if it's just before the night that the homeworks are due. As always, if you want to ask me questions, we could set up a separate office hour, or alternatively, we could, if you want to, Skype or Google Hangout or something. I could meet you any evening through Skype or Google Hangouts, or I won't say I can meet you any evening, but I'm willing to schedule appointments with you in the evenings as well, if anyone finds it useful. Even if you don't find it useful, I will schedule an appointment with you. The midterm is graded, have you finished the tables at the very beginning, at the top? Yes. Okay, so basically they've been all graded electronically. So thank you very much, first of all, for uploading them. You should see your grades electronically. It's basically like an assignment. And also each problem has essentially comments. So I graded some of the problems, and Dunsu graded some of the problems. You can see I tried to offer a lot of comments, or at least some comments that I thought. Some of the comments were things, however, like, please see the solutions. And I think that the solution offers an explanation. I offered in each of your midterms comments that were related specifically to the way that you did your solution. Here's the histogram of the midterm scores. The max possible score is 115, and here's the histogram. So so the max score. Do you remember what the maximum score? Well, actually, you calculated the final max score. What was the max score here? 96. And this is 115. Okay, so that actually, believe it or not, don't get depressed. Don't get worried. I know that in this class, most people are interested in getting like a 3.5 and above, because that basically means that it satisfies a core requirement. So with regard to what that means in terms of these grades, if you're sort of in this category on the right, you have no problem. You're in perfectly good shape. If you're in this category, I would try to do a really, really good job on the final exam. I don't remember who. I try not to associate names and faces with scores because I don't like to bias anything based on that. So I didn't look at the names when I was grading them. However, if you're in this category, maybe these lower categories, I think it's really important to understand what you did that wasn't clear in the midterm. And again, please feel free to come and talk to me. I mean, I'm here for you. You guys have not been exploiting as much as you could the resource, which is basically me, because my goal is for everybody to learn this material really, really well. I think this is material that you will find useful for you, not just in communications, but in so many different other fields, whether you're doing pattern recognition, machine learning, communications, or even computer architecture or other sorts of sociology. I think that this is just incredibly useful material, and it's important to understand it. And if something's not clear, please let me know. The most important thing is if I see that you have learned something, you will do fine in terms of the grade. So my grade, if you're worried about a grade or if you have any questions about it, my grade will be my understanding of, at that point I actually do associate with a face. And at that point, I will sort of decide based on what I think you've known, what you've learned. Because learning is really what we're in here for. I mean, what are we struggling to get our PhDs for anyway, and that's just to become better learners. And so our meta goal in I think every single one of these classes that you're teaching or that you're taking, and my meta goal in every class that I teach is to sort of help everybody become a better learner. That means more efficient and more accurate. And so all of these tools that I work on and the Canvas things and everything, I mean, I hope that actually helps with that. At least that's our goal. So with regard to specific details of the midterm and the specific problems, let me think. I mean, I think the first 4 problems people generally did okay on for the most part. It was the latter problems. Some of it I think it was just running out of time, but it is graded on a curve, and this is so not this kind of histogram is not unexpected. The issue with regard, I mean, again, so a lot of what is done on the exams is sort of, not asking you about rote memorization, but asking you to sort of derive new things or to think. And that's also something that's important to do. So when you study for the final exam, maybe you could even get together in groups or something, but try to throw new problems at each other. Try to throw new problems, because it's sort of a meta, again, it's a meta exercise. I mean, of course, you have your cheat sheets, and you should, everything, somehow you should get everything that we possibly spoke about in lecture slides, and everything on the lecture slides is there for you. I mean, nothing, including all of my annotations. So you have accessible material that people historically in classrooms have not had, which is the entire recorded lectures and all of the notes and the classes and everything that we spoke about. Every word is being recorded, except for lecture, whatever it was, 7, which the second half of the lecture didn't get recorded. But go over this material, and that should somehow be distilled into your 8.5 by 11 cheat sheets. And that's also going to be a learning process, because just by doing that, you're going to remember the material by writing it down. In past, something else about that, so in the past I've actually insisted upon it being handwritten. This year I didn't do that, but I think it's actually better to do it hand, because you just sort of get a intimacy with material better than if you do it with LaTeX or something. So you might consider, even though it's not required, you might consider just handwriting, because I think you might learn better. It sort of becomes a work of art. You can frame it, show it to your great-grandchildren someday. But in any event, let me ask one last question before I move on. Has anyone not seen their grade? Has anyone seen their grade?
I just checked on the website and it's not there.
So if you go to the thing that you uploaded, are there no annotations in that file? Because they're like little red typed marks. That's what we did.
I was looking at like the spreadsheet summary of the grades.
No, I would go to the assignment. This is new to me. Canvas is new to me, so I don't know what it looks like from your end. But if you go to the assignments, and it's the midterm assignment, so what we're going to do for the final is the same thing. In fact, this time, because this whole idea of scanning in the midterm and mailing it to you and having you upload it to the website, we're going to do exactly the same thing for the final. And that way we can actually grade it right away. We can start grading it right away, wherever we are. I can grade it on an iPad even. There's also no chance of lost assignments or anything. But and you get the feedback right away. But what was I going to say? A couple of things. So what we're going to do for the final is we're going to make an assignment, and the assignment is going to be due the day after the final exam. And that assignment is going to be upload the PDF file that we send you that contains your final exam. Now, the reason why we ask you to do that is because I think I mentioned this to you last time, we don't have the ability to upload an assignment for you. Only you, each student, can upload an assignment. Now, that's something that's a limitation of Canvas. And when I went on the discussion help boards for Canvas, there were a number of people who requested that the sort of owners of the class, faculty, whoever, that they are allowed to upload an assignment for a student, which actually makes sense because if somebody's sick or something, say, hey, I turned this in early, could you please upload this for me, or whatever. I think that should be allowed. But right now it's not, so we actually have to have you do it. So that means that after the final exam happens, what will happen is we will immediately scan it that day, and we will email you your final exam in PDF format. So you'll have it right then. You'll see what you did, as well as you'll have the solutions as soon as you walk out of the room. Hopefully that itself will encourage you to sort of look at the solutions. But in any event, what you should do as soon as you get that email is upload it to the Canvas thing, and then and then we'll be grading it on Canvas. So then getting back to your question, so if you go to Canvas, do you not see the little typed red annotations on your exams?
I just went on my iPad and I don't see anything.
I can re-download my submission, but it's just my...
It's something called Speed Grader. On our side, it's called Speed Grader. So we went in. Is there something that we need to sort of make them available or something? Or
You better not download your PDF, but you can just see your assignment on Canvas. Then you can see.
Yeah, well, that's because it's just we don't know how to see this assignment on Canvas. So anyway, if people would just get online on Canvas and poke around and try to see if you can find it, it's possible that there's some button that we need to press to sort of allow you guys to see it. So on our side, what there is there's something called Speed Grader, and we can actually write, we can mark on your finals, and that's what we did with typing and writing with like a pen-like thing, and that's where your grades are and the comments are. Since this is new, I'm sorry. I thought that in fact, I thought that you had already had access to it as soon as we started grading. So I thought you might even see the partial grades because some of the grades have been there actually for a week already. It wasn't until last night that was the grading complete. So anyway, technical glitch. We will solve this offline. Actually, no, you solve this. You're the TA.
Okay.
You figured out. What do they need to do in order to see? Okay, so let's do a little bit of review. So remember last time we started talking about communication, and we started talking about imagining ourselves. I mean, the reason why we do this in terms of imagining ourselves in the 1930s is to sort of get a sense of how, in some sense, revolutionary these ideas were at the time. When people, now we take digital communication completely and entirely, and error-free communication entirely for granted. But it's always hard after there's been a revolution, and when a new generation of young people, I mean, at this point, many, many generations of young people, I mean, the people growing up in the 50s were, exposed to these ideas early on. But imagine growing up in the 1910s and the 1920s, and you knew about communications, and you knew about electrical engineering, you knew about Morse code, you knew about analog circuits to some extent, and actually to a lot of extent. And then the revolution was that you could do error-free communication. And the idea of encoding signals in such a way that you could restore them in a way, even no matter what kind of signal it was, you could restore them in a way that was error-free. So the ideas were that were revolutionary. The idea of achieving perfect communication within a perfect communications channel. That was revolutionary. So sort of, is there an upper bound on the information capable of being sent under different noise conditions? And if you increase the rate, does the error rate increase? Now, rate is, for some reason, even though this sounds like it might be very simple, let me talk a little bit about rate for a minute. So by rate, remember in compression, I said this on last Thursday, but I want to say it again. When we were talking about compression, R was our rate, and we wanted a small rate, the number of bits per source symbol. if we are doing good compression, the rate is small. We're using few bits per source symbol on average. Okay? In communication, it's the opposite. It's the number of bits per channel used. So here's this channel, right? We've got this communications channel going over here. And every time we use the channel, how many bits do we get through? So we're using the channel multiple times. Thinking of it as like, it's like a message I can send, right? And every time I use the channel, I send a message. And the question is, how many true information bits am I sending? Now, the idea of rate is that, you know, I might add lots and lots of redundancy bits. Like I might have a real message, which is a 4-bit message, but I might add 17 redundancy bits. All right, and so in that case, the rate is going to be not very good, right? Because it's going to be 4 divided by 21. That's the total number of bits per channel used. On the other hand, if I can get by using the channel with no redundancy bits, then if I send a 4-bit message, error-free, then the rate's going to be 4 bits per channel use or something. Right? So in general, in communication, we want to have a high rate. And again, rate is measured in units of bits per channel use. Okay. So this point about increasing the channel over noisy, increasing the rate over noisy channel will increase the error rate. That was what was thought. And the idea and it was also thought that the only way to achieve error-free communication is to not communicate. You know, if you don't, it's kind of like false positives and false negatives. I mean, you can always get no false positives if you have no false negatives if you don't run an experiment. Right? So, I mean, it's kind of a silly argument. But when you think about this profile, we're going to see a lot of these kinds of plots where on the x-axis it's the rate, right? So this is, again, in units of number of bits per channel use. And the y-axis is going to be the probability of error. And you know, you might think, oh, okay, so to get down to 0 probability of error, I have to bring the rate down to 0, which means not communicating at all. And Shannon basically changed all that idea. And here's an example that sort of gets the idea. Now let's say that we're representing a signal by a sequence of numbers, which is not so hard to understand at this point. And we know from the Nyquist theorem, and maybe we have a certain amount of distortion, but we've got quantization distortion, and if we have a band-limited signal, we can sample the signal at least twice the highest frequency of the original signal, and all that kind of great stuff. And so therefore, basically, there's nothing inherently lossy about representing even analog signals with a set of integers, right? As long as you do enough integers. But now we want to communicate this thing, and let's say that we want to speak these numbers over, say, a noisy AM channel. So AM is like AM radio, like amplitude modulation radio. And as you know, does anyone even know what AM is anymore? So it's like, or is it only like right-wing Republican talk show hosts who use it at this point? Does anyone know?
Religious stations.
Okay, so the point is that there's nothing wrong with religious stations. It's the right-wing Republican stations that I'm against. So, but the point is that AM is noisy. So, like if you can listen to it, and every time someone says something, like you hear this static, right? And sometimes entire words will be masked by a noise, right? So you might say a number, and then there might be a noise, and you completely miss that number because it's just the signal-noise ratio becomes so low at that point that it's gone. So now imagine instead we repeat a number k times, where k is, basically every time we speak, we never say, I think I have an example in the next. Did I have the example? Maybe I'm missing this slide. But the idea is that I'm getting confused here. Hold on. Oh, something just crashed. It just crashed on me. Oh, but it started up pretty well. I guess it doesn't like changing pages. No, it doesn't like that page in particular. Okay, we'll go slow. There's a slide I wanted to say, but here's the idea. So you have a sequence of numbers you want to say over the AM radio, and you know that the receiver will very likely miss some of them. So you agree, you just say, okay, I'm going to say every number 3 times, or 7 times, or some number. And sure, the receiver ends up basically missing some of the numbers, but that doesn't matter because they're repeated, and the probability of missing all 7 of those numbers gets really, really small very quickly, right? Because let's say that there's a 0.1 chance of noise corrupting any one number that you say. Right? So you increase it, you repeat every number 7 times, and so the probability of missing that number is 0.1 to the 7, right? And then you can say, oh, that's too big. So rather than repeating it 7 times, you repeat it 15 times or 31 times or however many times you want. And the probability of error, which is having all repetitions of a given number be corrupted by noise, decreases exponentially in the length of the repetition. Right? Now, this is great because the probability of error goes to 0, but at the same time, the rate of communication also goes to 0. Right? Because think about it now. Let's say it's one of 2 numbers. I mean, so it's binary. I mean, it doesn't matter really, but let's say it's binary. So you repeat something. So for every 1 bit of information, you're actually sending out however long the repetition is, say 31. So your rate, maybe your probability decreases exponentially, but your rate is now 1 over 31 bits per channel use. Because remember, the rate is measured in the total information that you're sending per channel is. And every channel use, in some sense, is sort of like you were sending, 1/31st of the information, because you're repeating it 31 times. So this is exactly that picture that I showed you before, where in this repetition code case, in order to get the probability of error going down to 0, we need to make the rate also go to 0. And we can make the probability of error, we can achieve perfect communication effectively by having the probability of error be so small that the universe will sooner end than I will get an error. But at the same time, you're communicating very, very slowly, your rate of communication. So it's actually not a very useful thing. So this is called a repetition code. And the repetition codes have that property, which is that, I've got to do this very carefully so it doesn't crash again. The iPad has become very temperamental. Okay, it didn't crash. So, but do you get the idea? Okay, so any questions about that idea? So what Shannon showed is that if we choose the messages very carefully, they will still be identifiable at the receiver. In other words, and what's interesting is that the rate doesn't need to go to 0. Now the idea is the following. We're going to see a variance of this picture in a number of different contexts. So let's say, for example, we've got a 3-character alphabet we want to send over the channel. Right? So maybe the characters consist of these 3 symbols, which is maybe 1, 2, and 3. And whenever we send one of these symbols, there's going to be noise corruption, but with extremely high probability. Let's say that if we send symbol number 1, this is the set of possible messages we'll receive. Right? So let's say we say 1 on the AM radio again. So yeah, we might hear 1 corrupted by noise, but if 1, there'll be these will be all of the different versions of a distorted 1, and this stuff here will be all the different versions of a distorted 3. And similarly, this stuff here will be all the different versions of a distorted, whatever the other symbol is, which is 2. Right? And if these things don't overlap, in other words, if these 3 regions, this, this, and this, if they don't overlap, then actually we can still achieve perfect communication. Because any symbol here, even though it's not the number 2 anymore, we know that it must have come from a number 2. And any symbol here, we know that it only came from the number 3, right? Because there's no overlap. So that's basically the idea of how we're going to be able to do this. So on the other hand, this seems, you might ask, well, wait a second, this still has the same problem. This is, rather than having all of these messages that we could potentially send over here, which might be a very, very rich alphabet, we're only actually restricting the alphabet to be these 3 symbols, which we know happen to not have overlap based on understanding about the noise characteristics of the channel. It's like, all of this stuff, this fan-out stuff, that's really noise, right? But that's random. That's just going to be random. We don't actually know why that happens. We actually know the distribution, but we don't know, we can't really control it. So as a result, what we do is we find these 3 symbols, which we know have non-overlapping regions after they've been corrupted by the noise. But that's also going to restrict our rate. Now the question is, can we come up with a strategy by carefully constructing the source messages in a way that we can still receive, so we can still achieve a probability of error going to 0 without actually the rate also going to 0. And that's exactly what Shannon showed. This is the slide I thought that I had forgotten. This is the slide that talked about what I was talking about before. So let me just add a little bit of redundancy to the redundancy slide, which is that in AM radio, rather than sending 43519 and here 4 static, 5, 1 static, we would have a repetition code. In this particular case, it repeats it 2 times. So we would send 44335511199, and then we'd receive maybe 4 static, 3, 3, 5 static, static 1, 9 static. So even though there's 2 statics in a row, we know that the first static came from the 5, just because we've just agreed beforehand on what things are being repeated. In this case, the second static here comes from the first symbol of a 1. And we use the one that's not static, the one that we recognize, to actually do the decoding. And if that's not good enough, we can repeat it as many times as we want. And then this is the problem with the rate going to 0. So the other idea that was sort of more novel, it was revolutionary, was that when we send the signal, we don't send the signal, we send a description of the signal, and then we reconstruct the signal at the destination end. So in some sense, we can have an algorithm which then describes the signal. Like when you're talking on the cell phone to your best friend, you're talking on the, how many, raise your hand if you've recently spoken on a cell phone. Come on, raise your hand. I spoke on a cell phone this morning. So everybody. So when you're listening to that person on the other side, it's really not them anymore speaking. It is a reconstruction of a description of them speaking based on the code. And so basically what you do is you essentially take speech and you encode it basically by a description. Okay, well now the format does this, and now the F0 does that, and all this other stuff. You're not actually, and then what happens on the destination end, sort of reconstruct it. You say, okay, here's some algorithm and here's some description. It's very similar to, if anyone has done any music, MIDI. Although MIDI is not a really good example, but the idea is, you're not listening to the analog sound of a piano anymore. What you're listening to is just something that was created by describing which note was played when and how hard. Right? That's not really a piano. I mean, it's being reconstructed by the sound of the piano at the receiver end, but it's going to be a very, it's not really the same player anymore in some sense. It's only the same player to the extent that the description is accurate. The reconstruction leads to something that's distortion-free. So this is the same idea, that in the early analog days, people thought that in order to send a message, you needed to record exactly that message. LPs, where you etch a thing on a piece of vinyl. I mean, that today, it sounds like it sounds ancient. I mean, it's incredible how archaic that idea is, where you scratch the surface and it wears out and it gets little particles of vinyl in the air and everything every time. And you're like dragging this diamond needle, and this is horrible in certain ways. But on the other hand, that's what one thought would be the only way to sort of send and receive messages, was to record them exactly and not to encode them. And so that idea, also of course driven by the advent of computers, computers and computational engines and stuff was revolutionary. But then the last point here was that we're adding redundancy, but signals have redundancy in them. Like speech has lots of redundancy, and most signals have redundancy. Images have redundancy. When you have a noisy channel, you add redundancy in a careful way that's not for the sake of the signal at all, but it's instead for the sake of being able to reconstruct the signal at the destination end. So the redundancy that's added to a signal before it goes into a channel has nothing to do with the signal. And this is the idea of the joint source channel coding theorem. That the idea is that you could, for example, take a source, compress it down to its entropy, its true entropy, send over those bits, and then when you send it over to a channel, you add redundancy back in. But the redundancy that you add into the bits is completely different than the redundancy that you stripped out. The redundancy is for the sake of the channel, not for the sake of the source. From the perspective of the channel, all sources look identical to each other. It just looks like a stream of random bits. You don't care what those bits were, where they came from, whether they were music or sound or radar or some sensor or anything else. You care only that they're a stream of bits, and you need to somehow reliably get the stream of bits over to the other side of a communications channel. And therefore, you just add redundancy. And if these bits were compressed, truly uniformly at random, great. If they're not, great. I mean, you don't care. You just want to get these bits over. But the point is you add back in redundancy, but a very different kind of redundancy. That idea also was revolutionary. So is Morse code an example of this from the 1800s? Let me ask you this question. So remember, Morse code is that you have characters, symbol code, and you code each letter by a series of dots and dashes. And yes, the more frequent letters had shorter encodings, and the less frequent letters had longer encodings. Does this get at the heart of what we're talking about? In certain ways, yes. In certain ways, no. I mean, on the one hand, like the fact that you had dashes and dots, that was an analog signal, and the tone was tuned to a frequency over an analog channel that tended to be easy to hear even when the channel got noisy. So and then a dot and a dash, I mean, there was a certain amount of time that a dash and a dot lasted. And that's redundancy, right? How much time do you hear this tone? So in some sense, you're adding a little bit of redundancy in the sense of the time. And you could communicate faster by using shorter dots and dashes, but then the chance of error increased. But if you wanted to ensure you communicated, you would use really, really slow Morse code, long dots and dashes. But then, of course, the rate would go to 0. So that Morse code then doesn't get at that idea. Morse code also doesn't get at the idea of sort of encoding different signals. I mean, the thing that it was meant for is coding letters. No one thought of, for example, encoding a musical song, or at least not that I'm aware of. I mean, there weren't MP3 files. And anyway, if there were, it would take a really long time to send, like the latest performance of Duke Ellington from New York up here to Seattle back in the 1930s or something. That probably wouldn't be feasible. It was better to just have somebody trek across the country or something. So it's a little bit yes and no, but it really doesn't get at the heart of what I'm trying to say. Okay, so let's get into a definition. So by a discrete channel, we said that we're going to be using a random probability distribution to measure, to sort of be our model of a channel. Right? By the way, are there any questions? Is this really super clear? Is it too clear? You look anxious. Like I always tell when people start like saying, "Is he going to get onto it? This is so obvious." So raise your hand if this is completely obvious. What I'm saying. All right, raise your hand if this is too slow. Okay, it's too slow. All right. Okay, so let's just go to prove the theorem. Don't worry. If this is obvious, be happy because there will be plenty of opportunity to get confused soon. Okay. I want to make it such that at least there's a little bit of this class that's obvious. So here's a channel, a discrete channel. So what we're going to be using is basically a probability distribution for the channel. Okay, so P of y given x. This is our model. So for given x, we want to send x, and the distribution of y given x is the possible noise. And this is a discrete channel right now. The analysis is complex enough when everything is discrete. We'll talk a little bit about analog as well, but next quarter is really when we're going to get into like the Gaussian channel. And discrete memoryless channel means that time doesn't matter. Everything's the same at each time step. So every channel we use is going to be based on the same noise model. That of course, is an assumption, which isn't true in practice. But again, when you go to analyze something, the first thing you should do is make it very simple and analyze it in the simple case. Because if you make it too complicated, there's no hope you'll analyze it in the complicated case if you haven't done the simple case. So we're going to assume it's memoryless. And this, the other way you can look at this is that it's like a conditional independence statement, so that the output at time t is independent of all past inputs given the input at time t. So the only thing you need really for the output at time t is the input at time t. Okay. And this together is called a DMC, a discrete memoryless channel. Okay. And here's our model. So, we have some source on the left. And it goes to this whole module here, which is an encoder. And the encoder, as we're going to see, corresponds to a source coder and a channel coder. And these are, again, it wasn't at all obvious to people that these things could be separated in this way. It was thought that maybe you needed to have an encoder, a separate encoder for each source and channel pair. And the idea, that would mean that you would have, if you have n sources and n channels, you would need n squared encoders. But here it's basically saying that you only need 2n units, 2n modules, n source coders and n channel coders, which was great. Right? And then similarly, you have a channel which is noise. This is some sort of noise. We send a signal in with noise, and then we've got a decoder, which is sort of the dual of the encoder. And again, it can be separated. You can have a channel decoder and then a source decoder. So in some sense, we've already done the source encoder. The source coder is just an entropy compression engine. Just converts any source and compresses it down to its entropy. So this stuff, we've already done this, and we've already done this. Now what we're going to do is talk about this in the middle. Okay. So here's noise. In case it wasn't obvious, the noise is in bright green. That's noise. And don't ask me why font colors and choices were made. But some terminology. So the idea is that you have W source messages. So again, we're not paying attention to the source coder now. We're just talking really about the channel coder and the channel decoder. And we have W is a random variable over messages, and maybe there's n bits, so there's n to the n possible messages. And when we have an encoder, we encode it into channel symbols. So X is going to be our, actually I have bullet points for this. It's a channel symbol, so X is our alphabet for channel symbols, and we're going to be using a length n, we're going to be using the channel n times. So that means that we have a length n string of channel symbols, channel input symbols. Maybe we should call these guys channel input symbols rather than source symbols. And then the noisy channel distorts the input of the channel into a length n string of receiver symbols, yn. And usually we can assume it's the same. I mean, this is general, so we're assuming x and y might be different, but oftentimes they're the same. And then what the decoder does is it basically takes this length n string of channel output symbols, and this could be channel output symbols. And comes up with W hat, which is from the same alphabet as what W was, and it's one of m possible messages. And the idea is that if you get back the same message, then you're in great shape. And we have a probability, it's a discrete memoryless channel, so we have some probability distribution over source, over channel input symbols, or I guess source symbols in some sense. And then we have a joint distribution over this whole process by essentially taking the input, the channel input distribution, and then the channel. Now in this particular case, we have control over this, we don't have control over this. So this is fixed. And this is adjustable. Right. So we get to adjust the distribution over symbols that get fed to the channel. And we have to suffer from whatever noise the channel has. Okay, that's basically this point here. And P of X is our source distribution, and we get to determine it, and we get to optimize over it. So we have a source, which is governed by P of X, and a channel that transforms X symbols into Y symbols, and it's governed by this conditional probability distribution. And it looks like we are having our own channel communications problems now. These two items, P of X and P of Y given X, are sufficient to compute the mutual information between X and Y, right? So there's the mutual information. This is a well-known quantity at this point, right? Everybody should be very happy to see our old friend mutual information that we've known since the beginning of this class. Can everybody wave and say hi or something? Hi, mutual information. Those of you on YouTube, wave, please. All 400 million of you. So we can now write this in the following way. We can write it as a function of the two random variables, but it's also parameterized by the source distribution P of X. So that's really this stuff down here, right? And so it's parameterized by this source distribution right here. Now, remember from lecture 3, that function is concave in P of X for a given fixed P of Y given X. So it's a concave function in the source distribution. And this is actually really good news because what we're going to be seeing is that we're going to be optimizing over P of X for a given fixed channel because we want to, as you're going to see, we're going to want to maximize this. Okay, so here's something that I think is really important. So the rate of information flow through a channel is given by the mutual information in units of bits per channel use. Now this is something I remember thinking was confusing when I first saw this, so I made this slide specifically for those of you who think like I do. And that's basically, how could mutual information be information flow? You know, think about it this way. Y is a random variable, and X is something that reduces the uncertainty about Y. Remember, because mutual information is entropy of Y minus the entropy of Y given X. How much has the uncertainty about Y reduced? And so therefore, you can think about this as an information flow. It's like the number of bits that are being sent from X to Y on average. Okay, so this is our measure of how much, and it's in the context of channel capacity, it's in units of information flow. So if for a given fixed distribution X and a given fixed channel distribution P of Y given X, every time we use the channel, we will be sending the mutual information number of bits per channel use. And so that's why the units are given by this, in this context, in bits per channel use. So these will be our units of mutual information here in this context, in the channel capacity context. And then we define the capacity of a channel, the information capacity. Let's be very clear here. The information capacity here is the maximum information flow. So it's basically optimizing this mutual information function for a given P of Y given X. So P of Y given X is fixed, and we're optimizing it over all source distributions. Because again, we don't get to control the channel, but we do get to control the source distribution. Now there's going to be two types of capacities we're going to be talking about in today's lecture. One is the information capacity, which is this optimization problem. The other is sort of this idea of achievability capacity, which is really it's a rate that sort of allows us to communicate with vanishing small probability of errors. And then we're going to show these things are together. But don't get confused about these two types of capacities. So I guess hopefully if these slides are good, we're going to call this, for the most part, the information capacity C. So C refers to this first capacity. So it's the maximum number of bits per channel that can be sent. Okay. And again, the rate, this is just a definition, we already talked about this. The rate is basically the number of bits per channel use that are sent. Again, everything is in the same unit, bits per channel use. A lot of redundancy in today's lecture. Okay, so here's now relating this a little bit, slightly more quantitatively back to the idea of compression. Did we do this slide last time? I can't remember. I'm having deja vu. But anyway, let's go to this. So basically, for compression, we have this probability of error corresponding to being proportional to the e to the negative n times the exponent, the error exponent, which is e of r. And we had this picture which basically said that when we're doing compression, as long as the rates were strictly above the entropy, that the error exponent was strictly positive, and so therefore the error would die down to 0 exponentially fast with block length. But on the other hand, if the entropy was below, if the rate we were trying to compress at was below the entropy, the error exponent was 0, and so the probability of error would not die down to 0 exponentially fast. In fact, it would sit at 1. And so we saw that there was this phase transition, this critical point called the entropy, below which the error exponent would not die down exponentially fast with block length, and above which the error exponent would die down, the error would die down exponentially fast with block length. So something funny happens at the entropy. So now, going back to our 1920s picture, where we might expect that the only way to achieve a probability of error of 0 is to have a 0 error rate, which is what we would get with the repetition code that we talked about. What Shannon showed was, in fact, an analogous situation happens with communication. And this critical point is this point C that we've just communicated, which is called the information capacity. Basically, it says that the error, in this scenario where you're doing block communication, so basically you have a block of length n. And you've got some source message, and you encode it in n uses of the channel. And we want to know how many bits of information are we sending per channel use. Right? And we can actually talk about the probability of error. So we have a dual situation, a complete exact dual of the compression. It basically says that the following happens. That if we look at the error exponent, so remember this is the exponent of the error, of the probability of error of being able to decode error-free, to communicate perfectly in a noisy channel. It basically says that if we have a rate that's above this critical point of capacity, the error exponent is 0. So no matter how big the block length, you're going to get an error. Whereas on the other hand, if we choose to communicate anything below the capacity, the error exponent is going to be strictly positive. And if we use a long enough block length, or even a short block length, but basically as the block length increases, the error exponent, because it's positive, means that the probability of error is going to die down to 0 exponentially fast. And there's two ways of looking at this. One, we can look at the error exponent, which is on the right-hand side here, or we can also look at it in terms of just the log of the probability of error. That as the rate goes above the capacity, the probability of error is going to go to 1 very quickly. Whereas if we look at the rate, if the rate is below the capacity, if we're not trying to communicate, we're not trying to push too many bits through, the probability of error is going to be essentially 0 for long enough block length. And it's exponentially increasing to 0. So with a moderate-sized block length, we can make the probability of error effectively 0. And that's different than the repetition code. So what Shannon proved is that there exists codes that have this property in the 1940s. Sorry. The codes don't exist in the 1940s. In the 1940s, he proved that there exists codes that have this property. He didn't, in those papers, say how to find them. That was the tantalizing aspect of his research. But he did say that they exist. And that's the theorem that we're going to be proving. So it's exact dual to the entropy compression case. So the idea, again, is C isn't necessarily 0. like we saw in the repetition code case. We can still achieve, essentially, for all intents and purposes, perfect communication as long as we're not trying to communicate too fast with a noisy channel. As you do regularly when you send an email or send a photo or text message someone or post to Twitter about how much you love EE514. Right? Hash I love EE514A fall 2013. Right? That's the hashtag for this class, right? How much you love this class. So you do, I think, I don't know. I like this class. Okay, so any questions? Maybe this is a good time to pause. But are there any questions at all about any of this?
So who was the first person to show how to find the code that's...
Oh, it's still going on. People are still doing research on this in certain ways.
Well, like, who was the first... Shannon didn't show how to find new codes in his paper. Like, how long after that started?
Oh, it instantly started this revolution. And I think even in the late 40s and early 50s, people started demonstrating codes that had these properties. But it's been getting edging closer and closer ever since. I mean, the mid-90s, there was some revolution. There was a sort of mini revolution in the mid-90s with low-density parity check codes and turbo codes. And they achieved rates that were much closer to the Shannon limit. It's still the case that nobody knows a code that actually gets as close as Shannon says as possible. So it's still an open problem in a certain sense, and people are still doing research on it, coming up with new codes all the time. Getting them adopted in widespread use, and on cellular networks, that's another matter. That's an issue that involves many other issues besides the technical ones. But we're over time, things are inching closer and closer and closer. And there's many other issues associated with it, because channels can change and they can adapt, and there's all sorts of other real-world considerations. But still, it's, I think, the case that these sparse codes, like LWC codes and turbo codes, are the state of the art. It's almost 20 years later now.
I heard that hard drives, the error in rigid bits is like 1 to 2%, which seems really, really high.
Yeah, it's amazing how many errors that exist in the world that you don't know about thanks to encoding, redundancy coding. That's right. This is, I guess, that's another point maybe I should mention, is that we've been talking about this in terms of communicating from one place in space to another place in space. But this also exactly applies to commuting from one place in time to another place in time, where you save a file to disk and then you read it back later from the same computer. That's exactly the scenario we're in, because the disk will have errors. I mean, everything in the world is really analog, and the signals that are stored on disk or stored on an SD drive are analog. And so when you read them, there's going to be some errors, and somehow you need to still communicate. You need to read back the file without errors. And so therefore you need to put redundancy. You need to have redundancy there. So okay, so let's take a break. Okay, so we're going to start now doing a bunch of looking at some very simple channels. And we're going to draw the channels using a diagram that show the possible mappings from input symbols to output symbols. So here the channel input symbols come from an alphabet, a binary alphabet, and the channel output symbols come from a binary alphabet also. So it's the x and script x is equal to script y in this case, right? It's just binary. And remember, that means that every time we use the channel, remember, in general, we're going to be using the channel n times to send a message. We have one of m possible messages, and we want to use the channel n times to encode m messages, to encode one of m messages. And in this particular case, it's going to be a bit. Every channel we use, we send a bit, and that means we can send a 0 or a 1. And this is a very nice channel because it's a noiseless binary channel, and it says that when you send a 0, you get back a 0, and then when you send a 1, you get back a 1. It's noiseless, right? And it's binary. And here are the probability distributions. And maybe this is obvious, but basically you just get an input copy. And so we can reliably send 1 bit per channel usage. Right? So the rate we can get is 1 bit per channel usage. Right? There's no error. Now normally we can't reliably send one bit. But let's just compute the mutual information. So the mutual information is equal to the entropy minus the conditional entropy. But the conditional entropy is going to be 0, right? Because if you know y, you know x in this channel. Right? It's deterministic. And so the mutual information is just the entropy. And then so when we maximize the mutual information, when we want to compute C, that's just finding the probability distribution P, which maximizes the entropy, and that just gives us the uniform distribution. So the way to maximize the information rate through this channel is to use a uniform distribution, in which case we get 1 bit per channel. If we did anything less, we wouldn't be communicating at as high a rate. Okay. So this is the uniform distribution, which achieves that capacity. So then when we encode signals, we want to make sure that we use a 0 and a 1 equally. And this is sort of great for compression, right? Because if we just compress our signals, we know that once it's compressed, if we truly do compress it down to the entropy, we're going to have a 50% chance of a 0 and a 50% chance of 1, right, in the compressed representation. And why is that? That was on a problem set, I believe. Because if it wasn't, then it wouldn't be optimal compression. Right? Because anything that's slightly biased could be compressed a little bit more to something at lower entropy. So therefore, any compressed signal would be optimal for this channel. You don't even need to do any channel coding. The other thing to note is that if we did, for example, use this, say the probability of 0 is equal to 0, then that would mean 0 information flow. Right? We're not sending anything because we're always only sending 1 bit, and that doesn't communicate anything because no matter what the input is, well, you already know what the input is because the output's going to be 1. But you can't send anything. So here's another example of a channel. This sort of gets at the idea of that yellow picture that we saw a little while ago, where basically we have an input alphabet of binary, which is 0, 1, and we alphabet of 0, 1, 2, 3. And the idea is that if we send a 0, then with probability 0.5, we're going to get either a 0 or a 1 at the output of the channel. And if we send a 1, then with probability 0.5, we're going to get a 2 or a 3. But there's going to be no overlap. So if we send a 0, there's going to be 2 possible symbols we're going to get. And if we send a 1, there's going to be 2 possible symbols. But it's indistinguishable. Or I should say it's not distinguishable. It's distinguishable. It's impossible to have any overlap. And so this is actually also a nice channel. Now the reason this is also going to have a C of equal to 1. Why? Because at most we can send 1 bit per channel use. And that's again optimized by the uniform distribution over P of X, for P of X. Because we can't send any more information, because remember the mutual information is upper bounded by entropy of X and the entropy of Y. And the biggest value of the entropy of X is 1. The biggest value of the entropy of Y is, what's the biggest possible value of the entropy of Y? Yeah, 2, right? So, and it's the minimum of 1 and 2, so the maximum rate is 1, and we can actually achieve that by using a uniform distribution over X. So it's the same idea. So, if we know Y in this particular channel, we know X, and so we've got the entropy of X, and then when we maximize over that, we get a capacity, the information capacity of 1 using the uniform distribution. What about this channel? What's the capacity, information capacity of this channel? It just flips bits. It's going to be 1, right? If you rename the bits, does it matter? No. So this is a permutation. No information is lost. I would be very happy with this channel. Right? And you should be too. So in general, any permutation channel that basically flips the bits, but deterministically, no information. As long as you know the permutation, nothing's lost. Okay, so here's an important slide. Okay, so this is something that is not mentioned in the book, and but this is really important to understand what the book is doing. We've got a given function of x. Okay, And we want to maximize this function of x. So in order to maximize this function of x, we show an upper bound. We show that f of x is less than or equal to alpha. And then we show that x achieves that alpha. And that's sufficient to show that it's a maximum. Okay? So it's actually, we don't take a derivative and set it equal to 0 or all that kind of stuff. This is a different strategy for computing the maximum. We show an upper bound, and then we show an achieving. We know something that achieves it. And that guarantees to be a maxima for that function. So x achieves, in some sense, the upper bound of alpha for f, for this function f. And now we're going to be doing this with respect to channel capacity. So we want to compute the capacity, C, the information capacity C, by maximizing overall probability distributions. And that's sometimes hard and sometimes easy. I mean, in general, you have to set up an optimization strategy over a concave maximization, which isn't so bad, but in order to actually do this computation, we have to set Lagrange multiplier and do all this stuff. And we will generally be doing that sometimes, but oftentimes we don't need to if we can just show an upper bound and then pick out of thin air a p of x that achieves that upper bound. So what we're going to be doing is we're going to do this, but the important thing is follows. So this is the capacity, right? Is to take the max over p of x of the mutual information. That it's a maxima, but it's not the maximum, meaning it's not necessarily the only probability distribution that achieves the maximum. There can be other probability distributions. And from the perspective of computing the information capacity value, from the perspective of computing C, all we care about is finding any of them, right? I mean, using this strategy for finding the maximum, we find an x star, not the x star. We find one x star that does it. That doesn't mean that it's unique. Secondly, and this is also really important, if we were to actually encode with this, the one that we achieve as a result of optimization isn't necessarily the one that we would use to encode with. Okay, this is only for the purposes of computing C. Right? There might be another one that also gets C, which is a much, much better one to do channel coding with. So right now, we should just think of C as a result of a given optimization. C is the information capacity. We're going to connect C to a different notion of capacity, which we'll define, we haven't yet defined. So right now, I think it's safest, in order to avoid confusion, to just think of C as the result of an optimization problem. Like I said at the beginning, I showed you these plots, and I said, well, if we communicate above C, we can't do it. If we communicate below C, we can. I did that because I'm sort of giving you the final result of the theorem, but it's going to take us some work to actually prove those plots. And when we're all done with this, maybe Thursday afternoon at the end of class, or maybe next Tuesday morning, we're going to come back to those plots and see how we've been able to get there. So I already said this. All right, so I've already said this. So the C that we obtain as the optimization won't necessarily be the one that we use for the actual coding. Okay, here's a nice channel. This is called the noisy typewriter. Now, for those of you who don't know what a typewriter is, a typewriter is things that offices and academics and lots of people used to use back in the Jurassic era, when before the eras of computers. And the idea is that you would type on something that looked just like a keyboard, and a little hammer would come and it would slap a sort of piece of paper with ink on it and with a sort of a stamp, and you could actually create text in that way. And the things would all jam up together. I remember doing that when all of the keys would jam, and you'd have to take them out. But anyway, this is a noisy typewriter, and it's noisy because basically, if you type the letter A, then either an A or a B can happen. And here, unlike the other channel, there can be overlaps. So if you type the letter A, either an A or a B can happen. If you type the letter B, then either a B or C can happen. And if you type the letter C, then either a C or D can happen. And if you type the letter D, then either D or an E can happen, and so on and so forth, right? So basically, you can see that the colors that are sort of written here, this is a red-blue, sort of give you the possible sources. So there's ambiguity, right? So if you receive this B here, you don't know if it was either a B that was sent or an A that was sent. So you have to figure out what to do there. So how do we communicate perfectly? It seems like if this was the 1930s, you'd say you can't do it, right? You'd say, well, sorry, if I get a B, there's going to be an error because I know that it either came from an A or a B. So we have 26, is everybody clear on the channel? Okay. So we have 26 input symbols. And each symbol maps probabilistically either to itself or its lexicographic neighbor. How's that for a phrase? That's a very fancy way of saying what I just said. And here's the distribution. We've already said this. Each symbol has a chance of error, so how do we communicate with the error? So here's how we do it. We don't send all symbols. We decide, okay, we're not going to send all 26 of our input symbols. We're going to only choose a subset of the input symbols. So let's zoom back in on this picture. So, okay, I'm going to put a mark. Okay, let's say I decide I want to be able to send an A. But if I send a B, I know I'm going to have ambiguities. So what you do is sort of cross off B, and you don't send B at all. And then you just say, okay, well, I'm going to send a C, and I'm not going to send a D. I'm going to send an E, and so on and so forth. Right? And so what happens then is that if you receive either an A or a B at the receiver side, you know it has to be an A. If you receive a C or a D, it has to be a C. And if you receive an E or an F, it has to be an E. So I've now essentially used this channel, and I can communicate perfectly with it. But I've done something not good. What have I done? Or I should say, what have you done? What have we done? Reduce the alphabet, and that means what? The rate goes down. The rate goes down rather than what would have been if it had been a perfect mapping, if it had been a non-noisy typewriter, the rate would have been log of 26. But now I've reduced the alphabet by a factor of 2, so the rate has gone down from log 26 to log 13. So I can reliably send log 13 bits per channel use. 1 out of 13 messages, log 13 bits. But it's perfect, right? It's absolutely perfect otherwise. So this is the key. This is the key idea behind essentially all of this stuff, that basically we identify a subset of the source symbols that lead to non-overlapping channel output symbols. Right? Now, if I send A and C, then AB is non-overlapping with CD. And I think this picture shows it. So let's zoom in a little bit on this. So you can see that the grayed out versions of the symbols, the grayed out edges are not active any longer. So only the black edges are used. The grayed ones are not, because you're never going to send a B, you're never going to send a D. So it's just like the thing we've done before, we had before, except that we changed the subset. So the question, and that would be the way of encoding it. And so we'd have a uniform distribution. So the question is, what happens to C when the probabilities are not all 1/2? So what if the probabilities were, rather than say 1/2, 1/2 here, it was say 1/3, 2/3? What would happen to the capacity?
Shouldn't matter, should it?
Shouldn't matter. What do you think?
The mutual information is still the same.
Yep. Doesn't matter, right? Because again, you don't have overlapping outputs. It doesn't matter. In general, we're not going to have a uniform distribution over these regions. So remember this yellow bubble figure where each source Each channel input symbol led to this region of channel output symbols. We never said it had to be uniform. All we said is it has to be non-overlapping. So nothing happens to C. Let's compute the capacity slightly more mathematically. Here's how we would do it. We'd compute, well, here's the expression for the capacity. Here's just substituting in the definition of mutual information. If we turn that into h of y given x is equal to 1, because for a given x, there's going to be two choices of y under this particular thing, right? And so that's going to be 1, and then we know that the maximum is going to be log 26 minus 1, which is log 13. Okay. Everybody see that? So and then this maximizing distribution, this is the optimization which gave us the log 26. That's achieved using the uniform distribution. But again, this is not the distribution that we would use to encode things. That's the distribution that we use to compute the capacity. A much easier distribution would be to use a distribution that uses different symbols. Okay. So here's an example of that thing I said. The uniform distribution over x gets us the value c, but that would be a distribution for which it would be very difficult to do decoding at that rate. A much easier distribution would be just turn off, set to 0 the probability of b and d in every other letter. But then it makes decoding very, very simple. And it still achieves that capacity. So if we set that distribution, we'd put 0 probability on these alternates, we would still have h of y is equal to 26, and we would have log 13 as the capacity of the channel. Okay, so this next channel is really important. Any questions about this? I already said this. The next channel is the BSC, the binary symmetric channel, and it's used a lot. It's a good example because it basically says, you can have overlap and confusion. And it's a nice channel because it's parameterized by one value, which is p, and that's what makes it symmetric. Because if you send a 0, then it could be either a 0 or 1 received, and the probability of the same thing being received as what was sent is 1 minus p, and the probability of the opposite thing being received as what was sent is p in either case. So it's symmetric in that sense. It's symmetric about, I guess you always need to have an axis, or it's symmetric about this axis in some sense. Okay. So it's not obvious how to decode. Right? I can't use just one. I can't just send one bit, right? Because if I just send 0, we know that the rate is, that is going to be 0. We're not sending any information if we're always sending a 0. We're always sending a 1. But we're interested in computing the capacity of this channel. So here are the probabilities. I think that's sort of obvious. So like I said, yeah, right. It sort of captures some of the difficulties of more realistic and more complicated channels, even though this is still a fairly simple channel to analyze. And so we study it. So the question is, can we still achieve reliable, meaning guaranteed, or guaranteed is in quote, basically, again, it means that as long as the block length is long enough, we can achieve a probability of error below any threshold. Can we still achieve guaranteed communication, error-free communication with this channel, even though there's always some probability of error? Every channel use, probability of p, there's going to be an error. We're going to get the wrong bit. Can we definitely achieve error-free communication? What do you think? Just intuitively. So if I send a 0 with probability p, I'm going to get a 1. If I send a 1 with probability p, I'm going to get a 0.
Seems like if p is 1/2, you're going to have some trouble.
Very good intuition. If p is 1/2, you're going to have some trouble. So if for every bit you send, you're equally likely to receive the bit that you send and the other bit, that seems like it would be a problematic case. But what if p is not equal to 1/2? Maybe you could do something. Okay, it turns out that the answer is yes, as we'll see. So as long as p is less than 1/2, I mean, the greater than 1/2 is the same, but we're just going to, without loss of generality, assume that p is less than 1/2. If p is less than 1/2 and we ask for, we don't ask to communicate too fast, then we can achieve error-free communication without an issue. Okay. So any p is not equal to 1/2 is sufficient, but we're not going to talk about this. So the idea is, think about the asymptotic equipartition property. If p is not equal to 1/2, there's going to be this notion of sort of typicality, that for any given, if we have a long string of x's, there's going to be a string of y's that are sort of typical for that string of x's, and there's going to be a string of y's that are not typical for that string of x's. And so any of the typical ones are going to be the ones that have all of the probability, and any of the atypical ones are going to be the ones that have vanishing probability of 0. That end up getting probability of 0 if the block length is long enough. And if then what we do is we say, okay, for each string it turns out that if it's the case that our rate is not too high, we'll be able to find the sets of typical sequences won't overlap. But if the rate is too high, the sets of typical sequences will overlap. Does that seem like a viable way of doing it? Doesn't make sense at all. We've got half the class falling asleep, the other half of the class saying, we don't know what's going on. So,
what's the capacity?
Well, we have to communicate that, or compute that. We haven't done that yet. But we're just going to talk about how to compute the capacity. Let's do that now. But this is sort of introducing you to the intuition of how we're possibly going to encode. So let's compute the capacity. So it's the mutual information. Start from the mutual information. And that's just from the definition of the mutual information to get this bit here. We're just summing over x. Do the second part. Now, as soon as we have, let's look at this little guy here. As soon as we have h of y given x is equal to x, thanks to the fact that this is symmetric, this thing here is just h of p, right? Because once we know x, it's the entropy of y given x, which is h of p, and it's the same for all x. So basically, we've got this thing, and we're summing over x. But now we can get rid of the whole x business and turn this into h of y minus h of p. And that's less than or equal to 1 minus h of p. Okay. So what have we done? We've taken the mutual information and found an upper bound. And now we need to find a p of x that achieves that upper bound. And that means that this is going to be the capacity. Okay, first find the upper bound, next find the achieving p of x.
The one is from log to...
This is from the upper bound. So it's from y is binary, and we're just saying that this h of y, the maximum possibility of h of y is 1. Now, h of y is a separate random variable. How do we maximize over p of x to get h of y? That's something we still haven't done yet. But we say, okay, here's some upper bound. now can we find a P of X which makes the mutual information 1 minus H of P? And in which case that becomes a maximizing P of X, and then and it would mean that the capacity is actually equal to this. At this point, we don't know if it's equal to this. So to achieve an upper bound, we need H of Y is equal to 1. So to get H of Y is equal to 1, let's look at the probability of Y is equal to 1. And then let's relate that in the joint distribution based on what we can control, which is the probability of X. Okay, so that's just using the definition of conditional probability and marginalizing things out according to this joint distribution. We have the things that we can control, which is P of X is equal to 1 and P of X is equal to 0. This stuff here we can't control, which is the channel. Let's write it as a function of one variable and then two variables, because once we know P of X is equal to 0, that's the same as 1 minus P of X is equal to 1. So let's just write it in terms of P of X is equal to 1. So we have the channel variables. So this thing here is equal to 1 minus P. Probability of X is equal to 1 is equal to this. We have this thing here is equal to just P. And then lastly, we have the probability of X is equal to 0 is equal to 1 minus the probability of X is equal to 1. Okay? And just with a little bit of algebra, we can write this in this way. It's P plus 1 minus 2P times P of X is equal to 1. So what we want to do is find a P of X is equal to 1 that makes P of Y is equal to 1/1/2. And what value of P of X is equal to 1 will give us that? How about 1/2? Right, so if we set this thing, this is what we can control. If we set this to 1/2, then we're just going to get P plus 1/2 minus P, which is equal to 1/2. And that's going to be equal to this thing here. Right? So that basically means that we can get the H of, we use a uniform distribution. So a uniform distribution on X gives us an H of Y, which is also uniform, which actually, to be honest, is actually not so surprising. So therefore, we've achieved an input distribution that achieves that upper bound of 1 minus H of P, and this is the capacity, 1 minus H of P. Now, getting back to this question about what happens when the channel has P is equal to 1/2. When the BSC has P set to 1/2, we've got the capacity is 1 minus 1, which means we can't communicate at all. That's what it says, C is equal to 0. Maybe I have this written down. So that's right, when P is equal to 1/2, the capacity is equal to 0. So if it randomly flips bits uniformly at random, there's no hope to ever recovering the source message. However, what this seems to say, if we can show this connection between C and communication, which we haven't yet done yet, we have not yet done yet. And that's one of the things that I don't think the book really makes clear. Because the book goes through and starts talking about all of this C stuff. And you're saying, well, wait a second, you haven't told me how to code yet. How do I know I can communicate if C is greater than 0? We haven't done that yet either, but at least we're admitting to you that we haven't yet done this. We haven't made the connection between C, the value C, which is really like the information capacity, and the communication capacity, which we still haven't even yet defined. Okay, but we're telling you that we're going to define this, and we're telling you that this C is going to be the same as that communication capacity. So what this means is that as long as P is not equal to 1/2, we can communicate, but potentially slowly. So let's say that P is very close to 0.5, like 0.499. Then it's going to be, it means that we can use 2.8 times 10 to the negative 6 bits per channel use. So it basically means in order to communicate 1 bit, we need to use the channel 2.8 million times to communicate 1 bit of information. So that's a really noisy channel, right? I mean, it's basically saying that most of the time you're going to get a random thing. But if you're willing to use the channel 2.8 million times, I can send a bit through.
why can't we do it this with P equal to 1/2 with the same, just communicate slowly?
Because, well, what intuitively, there's an intuitive explanation, there's a mathematical explanation. When P is exactly equal to 1/2, and we receive something, there's an equal chance, exactly equal chance, that when we receive a 1, it could have come from a 0 or a 1. We have no way of knowing. Absolutely no way of knowing. If there's even a little bit of bias in the channel, like 0.499, then we can eventually, after we use the channel enough time, make a reliable estimate of what bit was intended to be sent. Right? But if it's exactly with the 0.5, there's no way. It's just lost. The information is lost. It's too noisy. But, you know, the rate would be really horrendous if it's so noisy. I mean, what this is saying, however, is that it's still possible to communicate, even though you have such a noisy channel, 0.499, it's still possible to achieve perfect communication with extreme noise conditions if your rate slows down. But it doesn't go to 0. That's the critical thing. The rate is capacity. If P is equal to 0 or P is equal to 1, the capacity is 1. In fact, if P is equal to 0, then basically what happens is it just cuts all this stuff off, and we get back that other channel that we saw earlier, where just 0 goes to 0 and 1 goes to 1. Right? And that's, so the capacity is reflected by this. When h of P, when P is equal to 0, then h of P is equal to 0. And or we had the permutation guy. And when P is equal to 1, it's the permutation channel. So. Okay, let's talk a little bit about decoding. I mean, we're not really going to talk about decoding. I mean, that we could have another quarter of class time just on encoding strategies and decoding strategies, because we don't have actually, the information theory really should be a 3-quarter sequence. And if I always say this, so if you really want to take a class on coding theory, you should demand the EE department create a new class on coding theory. But that would take us too far astray, because in terms of searching for the right code, and then get into codes on graphs, and it'll be low density parity check codes. But let's just talk a little bit about it for a minute. So we can decode using sort of maximum likelihood decoding, which basically says the following. We form this probability distribution, P of x given y. For those of you, by the way, who are interested in pattern recognition, or things like speech recognition and other things, like the word decoder in speech recognition comes from information theory based on this exact problem, because the idea is that speech is sort of an encoded version of some text message, and so you're decoding it back into its original form, which is the text message. So we have a probability distribution P of x given y, which is comprised of a channel, which is the noise, a source distribution, and then a marginal over y, which is based on summing out all inputs to get P of y. So one way of decoding is compute this thing, compute P of x given y, and then compute the argmax. Like y is known, we receive a channel output symbol y, and then we find, based on this probability distribution, the x that has highest conditional probability. This is called maximum likelihood decoding. And this is, by the way, also optimal decoding. It's optimal in that it minimizes the error. Why does it minimize the error? Because the error, in this case, I don't know if I have this written down. Let me just write it up. Probably, this happens a lot. I forget what's on the next slide. I write it down, and then I flip the slide, and I realize that it's on the next slide. Let's see if it happens. The error is not, that's not the one I wanted. So the error, basically, the error in deciding x is equal to 1 minus P of x given y. I put a bar over y, because basically we know y, and any particular choice x as what was sent has an error, which is this. And if we choose the x that has maximum posterior probability, that minimizes the error. So this is another way of looking at the error. The error is basically the probability that the decoded signal x hat is not equal to what was sent. Yeah, actually I do have it. So this is minimal error. So if we choose this, does everybody see this? So if we choose x according to this way, it minimizes this error. Now, in general, computing maximum likely decoding, this is a very, very difficult problem. It's not so easy as just like if it's an integer and if it's just a binary, then you would just say, oh, just try both. But in general, x can be a giant multivariate probability distribution. And let's say that x was length n, and even if the symbols were binary, then there would be 2 to the n possible choices. And you can't just iterate over all 2 to the n choices, finding the one that's maximized. And so the problem of probabilistic inference is a huge problem that people in information theory and in machine learning and in statistics have been working on for many years. And it's, in general, NP complete, so you can't expect to be able to do it in general in polynomial time. And it's therefore meaning doing the optimal decoding, minimum error decoding, is likely to be exponentially expensive unless p is equal to NP. We don't know if it's exponential or not. But most people believe that p is not equal to NP. Now there are many things that you can do in practice that are much better, or that are practical. Like there are many approximate inference strategies or approximate maximum a posteriori decoding strategies that, while they're not guaranteed to minimize the error, they generally tend to do pretty well. In fact, one of the things that's so great about turbo coding and LDPC, low density parity check coding, is that the codes are such that algorithms for approximate inference tend to be accurate. So that's one of their benefits. So loopy belief propagation is another strategy where you send messages around a graph that describes the probability distribution. These are all things that we're not going to talk about here, but graphical model inference is a topic that's typically done in machine learning, but it was actually originally done in information theory. In fact, Bob Gallagher, who was an information theorist from MIT in the 1960s, came up with LDPC in the early 60s. And basically, it was a form of loopy belief propagation. But at the time, in the early 60s, he didn't think it was useful. So he wrote a paper about it, and then he forgot about it. And it wasn't until the mid-90s was it rediscovered, almost 30 years later. And quite amazing. And it was discovered to be something very similar to what people in machine learning and artificial intelligence were doing, like Bayesian networks, things like that. But let's move on a little bit. Are there any questions about this, though? Again, we could have a whole topic on doing probabilistic inference. In fact, I've in the past taught a class on graphical models, which talks about how do you do inference fast. And there are whole issues of transactions on information theory devoted to codes on graphs, where you write a graph, use a graph to represent probability distributions, and how do you decode on them. So any questions? Okay, let's talk about another channel. This is called the binary eraser channel. So basically, with probability alpha, we lose the bit. And it goes to some symbol E, which means nothing. It just means it's lost. Whereas with probability 1 minus alpha, the bit that we want to send has been sent. So we want to compute the capacity of this channel. And obviously, it should be obvious at this point that it's a function of alpha. We can't talk about the capacity without alpha. And if alpha is equal to 0, we're going to have a capacity of 1. Also, obviously, because then we get back to the situation we were in before. So let's go ahead and start chugging away on this. We do the same thing we did before, represented in this particular way. Now, if we know x, then again the entropy of y is going to be just entropy of alpha. Right? So that part becomes not part of the computation anymore. So is everybody happy with me going from this step to this step? And those of you who are not nodding your head? If you know x, remember it's the average, right? So if I know that if I find out that x is equal to 1, I've got alpha 1 minus alpha. If I find out that x is equal to 0, I've got alpha 1 minus alpha. Take the average, it's going to be the entropy of alpha. So the only thing that matters in the uncertainty, once given x, is going to be alpha. Okay. So we do have also an upper bound on y, on the entropy of y, which is log 3. Okay. So let's do this in this following way. So let's define this new random variable, which is e, which is a binary variable which is true whenever y is equal to the erasure symbol. So then we compute h of y, which is equal to h of y comma e. And why is that? Well, because e is a deterministic function of y. We know y, so it doesn't add any uncertainty, so it has the same uncertainty. Okay. But it's still a separate random variable, and so we can write it as the entropy of e plus the entropy of y given e. Right. Now let's just, for simplicity, let pi be the probability of x is equal to 1. Then the entropy of y is going to be the entropy of this three-dimensional probability distribution here. It's either going to be, if y is equal to e, the probability of that happening is alpha, right? If y is equal to 0, that happens with 1 minus alpha and the probability of x being 0, which is this. And if y is equal to 1, that happens with 1 minus alpha, meaning it wasn't an erasure, and the probability of x being 1. So those are the three probabilities. Just broken, sort of decomposed in this way into these two different forms based on pi and alpha. Now this actually then is equal to h of alpha plus 1 minus alpha times h of pi. And then this follows for the following reason, because when we look at, well, first of all, we have h of e here is equal to h of alpha, right? Because e, if it's true, it happens with probability alpha. If it's false, it happens with probability 1 minus alpha. This next bit is the conditional entropy. And the conditional entropy can be written as when there is an erasure, which is the probability of alpha times the entropy of y given when there is an erasure versus the entropy of y when it's not an erasure. And there's a typo here. Let me fix this. This is y is equal to e. So when there's not an erasure, then the entropy of y is just going to be equal to the entropy of pi, right, which is the source distribution. When there is an erasure, then we know the value of y, right? There's only one choice. And so this whole thing is going to be equal to 0. This whole thing is going to be 1 minus alpha times the entropy of pi. So therefore, we get that this conditional entropy here is equal to this part. Okay, I'm not done yet. But we get something which has the following form. We have a nice way of writing entropy of y in terms of the thing that we actually care about maximizing over, which is pi. Right? So the alpha is sort of a constant with respect to the optimization. And we just then maximize over pi of 1 minus alpha times h of pi. But then that basically is just 1 minus alpha. And that becomes the capacity. So therefore, when alpha is equal to 0, we get a capacity of 1. When alpha is equal to 1, we get a capacity of 0. And it goes down linearly, or inversely linearly. And the best capacity is achieved when pi is equal to 1/2. So again, it's a uniform distribution, which is the achieving distribution. It's a achieving distribution, I should say. And this actually makes a lot of sense, I think, because alpha % of the bits are lost. So when you think about a long block length, it makes sense that the capacity would go down a fraction alpha from 1. So this makes enormous intuitive sense. Okay, here's another one, the ternary confusion channel. Let's talk about this next time, because I think we're running out of time. But so basically what we're going to do, as you can sort of see up here, I've prepared these slides deliberately for everybody to sort of look at. We've got a bunch of properties of the channels. We've got the joint asymptotic equipartition property and the actual proof of Shannon's second theorem. So everything that we're going to talk about on Thursday is already in the slides, because I wanted it to be such that you could read ahead in the slides. So we will start with additional properties of channel capacity on Thursday. But please do try to read ahead, because when we go through this proof, it will be much clearer if you've actually had a chance to have skimmed through them beforehand. And I think that's all I want to say. Are there any last questions? Any first questions? Okay, I will see you later.